Solving radical equations graphically. We'll do it graphically, but we'll also uh, do it algebraically. Some review. Radical equation has a variable under a radical sign, the root symbol. Extraneous roots. They are roots of the equation that were obtained after squaring, but they are not the roots of the original question. Steps to solving a radical equation algebraically. 1. Identify any restrictions on the variable. Remember, when multiplying or dividing both sides of an inequality by a negative number, you need to reverse the direction of the inequality sign. So here's an example, but a much simpler example. I know 5 is less than 7. What if I multiply both sides by -1? This will illustrate why we reverse the sign. So now I have -5 is less than -7. No, it's not. It's greater than. So that is why the rule is there. When you multiply or divide by -1, you always reverse the sign. Okay, so this is using real numbers as an example, but there's the other example. Okay, so when you look for restrictions on the variable, you take the radicand, set it greater than or equal to 0, and solve for the inequality x. And that's your restriction. So this is your restriction. 2. Isolate the radical on one side of the equation, square each side, solve the resulting equation. You might need the factor or quadratic formula. Check for extraneous roots and reject them. You must check all answers. Okay. Example 1. Relate roots and x-intercepts. Determine the roots of the equation 2 times square root of x minus 4 minus 3 equals 0. Well, I'm going to isolate the root. I'm going to isolate the radical before I square it, right? Remember, squaring is our path to solving this. So I'm going to add 3 to both sides. I'm going to square both sides instead of dividing by 2, and I'm going to square 3 halves. Let's just leave it like this, and I'm going to square both sides. So this is what it looks like. 2 times the square root of x minus 4 squared equals 3 squared. So I have 4 times x minus 4 equals 9. Divide both sides by 4. I have x minus 4 equals 9/4. I have x equals 9/4 plus 4. X equals 9/4 plus 16/4. X equals 25/4, or 6.25. All right, let's keep that in mind. Okay, so the x-intercept is 6.25. Using a graph, letter B, state the x-intercepts of the graph of 2 times square root of x minus 4 minus 3 equals 0. Method 1, graph a single equation. So if I look at it like this, and I graph this, so that's at 4, -3, and 6.25, 0. This is what it looks like. Something like that, folks. Okay, so this is your y-axis, x-axis. y1 equals 2 times x minus 4 minus 3, and then my 0 at 6.25, 0. All right, graphing 2 equations. So when I do the 2 equation graphing method, y1 equals 2 square root of x minus 4. y2 equals 3. And I'm going to graph each of these and then look for the intersection point. So this is y1. Let me do y2 in blue so we can clearly see it. y2 equals 3. And so this is y2. And then what is that intersection point? This intersection point is 6.25 and 3. And then the solution comes from the x value, which is 6.25. Okay, so we're relating the two methods. Describe the relationship between your findings in part A and B. The solution, so algebraically and graphically, the solution of the equation in A is the same as the x-intercept in B, method 1. Also, the solution is the same as the x value of the intersection point in B, method 2. Next page, let's do another example. Example 2. Solve a radical equation involving an extraneous solution. So solve the equation 3 plus square root of x minus 1 equals x algebraically. Verify your answer graphically. So I start with 3 plus square root of x minus 1 equals x. I need to isolate the radical, so I'm going to subtract 3 from both sides. And then let's square both sides. I have x minus 1 equals x squared minus 6x plus 9. Let me solve for x by isolating x. So we're going to have a quadratic here. I will have 0 equals x squared minus 7x plus 10. 0 equals x minus 5, x minus 2. X minus 5 equals 0. I have one solution, x equals 5. X minus 2 equals 0. I have another solution, x equals 2. Let me check for restrictions. So x minus 1 must be greater than or equal to 0. X must be greater than or equal to 1. Well, here's my restriction. Right now, both of these meet that restriction, but let's check our answer. So check. I'm going to check x equals 5. So 3 plus square root of 5 minus 1 equals 3. Oh, so sorry, 5. 3 plus square root of 4 equals 5. 3 plus 2 equals 5. 5 equals 5. That's a check. Let's check x equals 2. I have 3 plus square root of 2 minus 1 equals 2. 3 plus square root of 1 equals 2. 3 plus 1 equals 2. 4 does not equal 2. So this is extraneous. So I'm going to reject x equals 2. Graphically, let's take a look at what we got. So I'm going to graph y1 equals square root of x minus 1. And then in blue, y2 equals x minus 3. So I'm going to take this part and I'm going to separate it into two separate graphs, and I'm going to see where they intersect. So when I graph this, folks, it's going to look something like this. So y1 is going to be like that, and then So this is y1. y2 is going to be something like this. Okay, and then here's our intersection point. X equals 5. The actual point, if you do the intersection, is 5, 2. Okay, we of course want that x value, so there's my solution. The x equals 2, you'll see that x equals 2, there is no intersection point. Hey folks, I just wanted to go back to example 2. This is beyond the scope of what we would do in class, but I thought it'd be interesting enough to take a look at example 2 and ask the question, why are there extraneous roots to begin with? If you ever wondered that. Well, let's take our example 2. I have 3 plus square root of x minus 1 equals x. And a slight modification, I'm going to isolate the radical like this. And when we look at this, in this case, we're really only concerned with the positive square root version, right? When we think about this, and I'll show you this with a Desmos example, in reality, what you should be looking at is positive and a negative version of the square root. And that really is the key to understanding why there are extraneous roots. Okay, let's set that one aside. I will talk about another reason why we are creating or why we have an extraneous root to begin with. So if we think about the next step, right? The next step is we're going to square both sides. What happens when we square both sides? Right? We're doing this to eliminate that radical, but think about it this way, right? When we square both sides, we are creating a situation where we are now having extraneous roots. Why? Let's think about this. If I just have the simple statement a equals b, and I square both sides, a squared equals b squared, well, that's true, right? So if I pick the number, let a equals 3, 3 squared equals, well, that also equals b, so equals 3 squared. That's true. This is also true, folks. Negative 3. If I say a equals negative 3 equals b, this is also true, folks. Hey, here's the problem when we square something that has a radical involved, right? When we square something, it's not reversible. If we unsquare it, meaning we take the square root, we're changing the math that we're doing. That's kind of the easiest way to think about this. So let me write it this way. Let me say this time negative 3 squared equals positive 3 squared. Well, 9 equals 9. That's still true. But here's the problem. If I reverse this by saying the square root of negative 3 squared, square root of that is negative 3. Square root of that is 3. That's not true. So this is false. So this squaring operation, I cannot reverse it and get a true statement. And this is in essence why we have extraneous roots. When we do this operation, we're squaring both sides. If I rewrite this, folks, as square root of x minus 1 squared, well, this is one way I can write it. Think about this one, folks. If I do this, this is still true, because if I square this negative, I get a positive. But take a look at negative square root of x minus 1. Let's graph this and find out what this looks like. So if I back this out, if I do the square root of negative, if I take the square root of all of this, this is my result. I get negative square root of x minus 1 equals x minus 3. Remember that extraneous solution? We said x equals 2 originally was extraneous. Well, if I plug this in, it is now a solution. But in the problem itself, we considered only the positive version. And that's the rule when we are solving radical equations. Let me hop on over to Desmos and show you graphically, and it'll make a lot more sense. Hey folks, over at Desmos. So remember we had example 2, the equation is 3 plus square root of x minus 1 equals x. So we split that up into y equals square root of x minus 1 and y equals x minus 3, right? This gave us a handy way to solve for x. And if you look at the intersection, right, we said x equals 5 was your solution. So let me anchor that. So there's my solution. That's my solution. And remember I said that in the explainer just before this, right, when I wrote it out, that we need to consider the negative version, right? So when you have a radical and you square it, and then you unsquare it, meaning you go backwards and go back to the radical form, right? It's not the same operation going forwards and backwards. And we showed that algebraically, right? And so we have to consider the negative version, right? So it's like we take this and then we reflect it across the x-axis. So I do a -1 here, right? Look what happens when I do a -1. And remember I showed algebraically that the extraneous solution x equals 2, it works if you consider the negative version of this radical. So is that true? Well, let's take a look. Well, there's x equals 2. If I label that, this was what we label as extraneous, because when we're solving radical equations, we're considering the positive version of it only, and just by definition, right? So I'm going to put a dotted line on this, like this, to show you that it is in fact extraneous, right? So you can clearly see here, let me just zoom in. Just to recap, if I start, right, I started with rearranging the two equations and finding the intersection point, and the intersection point is 5, 2, which is our solution, right? So solution is x equal 5. Okay, so we know that. And then we said we have to consider this purple graph. There's actually a negative version to it. When we square it, right, in essence, we are essentially creating a negative version. And there's the negative version in dotted purple. And when we look at where it intersects right at the extraneous value of x equals 2. And this is a visual explanation coupled with the algebraic explanation of why we have extraneous values. Example 3, approximate solutions to radical equations. Just as an aside, this example 2, I'll show you on Desmos that will help you visualize why x equals 2 is not a solution. Okay, let's move to example 3. Approximate solutions to radical equations. Solve the equation x plus 3 equals square root of 12 minus 2x squared graphically. Express your answer to the nearest tenth. Okay, so when I graph this, there we go. And then, let's see. You're going to get something like this, like a dome. And this is your y1. So y1 equals square root of 12 minus 2x squared. And then y2, we're going to get an intersection like something like this, folks. This is y2 equals x plus 3. And what are my two intersection points? And we're going to get approximate values. Let's see. Let me give you my window settings. X is negative 2.5, 2.5, and 1. And my y is negative 2.5, 5, and 1. And the first intersection point, negative 2.41 and 0.59, rounding of course, and this one is at 0.41 and 3.41. So intersections at negative 2.41, 0.59, and 0.41 and 3.41. So my solutions are the x values. Negative 2 point approximate, right? X equals negative 2.41 and 0.41. Let's solve this algebraically. I have x plus 3 equals square root of 12 minus 2x squared. The radical is already isolated, so I'm going to square both sides. I have x squared plus 6x plus 9 equals 12 minus 2x squared. Let's make everything equal to 0. Collect like terms. I have 3x squared plus 6x minus 3 equals 0. Factor out a 3. I have x squared plus 2x minus 1 equals 0. I'm going to need the quadratic formula for this. So x equals negative b plus or minus b squared minus 4ac over 2a. So x equals negative b, which is 2, plus or minus b squared, that's 2 squared minus 4, times a, which is 1, times c, which is negative 1, over 2 times a, which is 1. That's negative 2 plus or minus 4 plus 4 divided by 2. That's x equals negative 2 plus or minus square root of 8 over 2. X equals negative 2 plus or minus 2 square root of 2 over 2. That's x equals negative 1 plus or minus square root of 2. So x equals negative 1 plus square root of 2. that's roughly 0.41. X equals negative 1 minus square root of 2. That is roughly, rounded to the nearest hundredth, negative 2.41. So does that make sense? Sure does. All right. Algebraically, graphically. Okay, last page, folks. Application. Okay, an engineer designs a roller coaster that involves a vertical drop section just below the top of the ride. She uses the equation V equals velocity equals the square root of the initial velocity squared plus 2 times AD to model the velocity V in feet per second of the ride's cars after dropping a distance d in feet with an initial velocity V naught in feet per second at the top of the drop and a constant acceleration in feet per second. So acceleration, this will be your A value. Determine the initial velocity of the roller coaster to the nearest tenth if the velocity will be 85 feet per second at the bottom of a vertical drop of 111.5 feet, and the only acceleration is due to gravity, which is 32 feet per second squared. Wow. Okay. I have my original equation. Velocity equals the square root of initial velocity squared plus 2 times acceleration times the vertical distance. I need to solve for V naught. V, velocity equals 85 feet per second. D, vertical distance is 111.5 feet. Acceleration is 32 feet per second squared. So let's plug all that in and solve for V naught. So I have 85 equals square root of V naught squared plus 2 times A, which is 32, times D, 111.5. Let's square both sides. Oh, let me do this actually. 85 equals square root of V naught squared plus 7,136. I'm going to square both sides. That is 7,225 equals V naught squared plus 7,136. Subtract 7,136 from both sides. I get 89 equals V naught squared. And V naught equals 9.4 meters per second. So we wanted determine the initial velocity to the nearest tenth. So 9.4 meters per second.